Okay, so in this video, we're going to look at generalized linear models as part of our course ST4 on linear models. So this is demonstration video number 7, looking at that area. So remember, we're looking at a generalized linear model, which is a model with a more specific error distribution in terms of looking at its predictor variable y, and that's a function of maybe x plus other factors, possibly z, and the interaction then of z and x together as well. So we can model all these things too if we wish. There are many other model classes, generalized additive models, linear mixed effects models, and so on, that we're not really talking about here. So we're just talking about the very basics of GLMs when using RStudio. So in that, we're looking at is basically having our formula here for our model of interest, and then choosing a family of distributions from which we can use to model our data. So for example, we have a structure like this where we're saying y tilde x plus z is our formula for the model, and then we're selecting a method of binomial. And it's a variety of different methods that we choose for a binomial distribution because we have two binary categories for y. That's looking at a logistic model. So it's kind of a classification approach. We have a Gaussian family, gamma family, inverse Gaussian family, Poisson family, which is effective for biological data, uh, uh, crazy normal model, crazy binomial model, crazy Poisson model as well. There's quite a few options. And all of these are going to try to, for those that are binomial logistic or logit regression models, that are going to predict a binary outcome based on a series of input variables. And we're going to look at the Poisson model as well, where we're dealing with positive integers only, which is so often what we encounter in biological data sets. So what we're going to do now is switch over to RStudio, where we'll look at this in more detail. So what we're going to do is use our existing data set of heights and weights, and that is the basis on which to create a large number set of heights and weights as well. So here we have 50 heights and 50 weights, and we can even do a histogram. These are the same as ones we've used before, just to get a sense of what they look like. What we're going to do is add another factor as well called hydration 50. So creating 50 values there based on heights and weights, the ratio of the two. And if we look at a histogram of the hydration, we can see we have a kind of tight distribution of values there. And we can look at the extent to which height and hydration are correlated or not correlated, and same with weight as well. So you can see there, both those values are small, suggesting that it may not have a big effect. But anyway, let's model this as a Poisson distribution, where we have a simple model where we're predicting the weight based on the height, like we did before. So this is a very simple model, and what we can do then is use this summary function. Oh, we have negative values. Okay. So what we can do here, this is a good point. When we're dealing with negative values in Poisson distribution, that's not going to work. So we can see with hydration 50, that has no negative values that we can see. Whereas for, we look through the histograms, weight 50, we have one negative value. So what we can do is increase the mean weight. So we just put a factor plus 10 here. Let's increase the mean weight. We got a new data set there for each of them. See the correlations are both kind of negative. We run our Poisson model predicting weight. And then we get the summary of that. And what we can see from the summary is that we have the intercept has a relatively small standard error, indicating the intercept has a strong effect, whereas the height has no substantial effect at all. You see as well that we have the null deviance mentioned down the bottom. That's the prediction of model-based intercept only. The residual deviance includes the prediction of the model or factor y based on x as well as the intercept. You can see that there's no difference between the null and residual, indicating that there's no input into our model from the height. It does not work in our model. It doesn't help. If this value was further apart, we could measure it as if it was a chi-square distribution with 1 degree of freedom in this instance, because we just have one parameter. But we don't need to do that. I see that as well, that actually information criterion is infinite, so that doesn't really work for Poisson models. If we had a more complex one where we're going to add we can back transform this to get the intercept and then the height. So you see the height of value for 550 is close to 1, indicating it's a very small effect, whereas the intercept is large. If we do it from a complex model, including hydration 50, we can see that our summary now, we get an estimate of hydration as minus 1.4 and a standard error that's very similar in terms of magnitude, indicating it has no substantial effect. Supporting that, we see that the residual deviance is quite close still to the null deviance. It's slightly further away, indicating that the hydration 50 has some effect on this, but it's not substantial. We can back transform to get those values again. You see the height 50, because we include a new factor, has changed slightly. And hydration 50 is another value as well that we can incorporate into our model. So we see here that this kind of Poisson just model fitting did not work well for data, perhaps because it's not very correlated. So let's try new data. There we have a stronger association. So let's try that for the binomial model. Here we've got a simple model where we've got a random, largely random repeating factors of zeros and ones 25 times, which are predicted by height 50. So there's no evidence that there'd be any association here, but let's see what the model says. We can look at a summary, and you can see there we have for the intercept, we have an estimate and standard error that is similar, so we get no strong association, and same for height 50. And that's supported by the null and residual deviance. We can look at the other comparison with the GLM2 for a complex model, including hydration 50. Let's see if this is better. And again, our summary will tell us that the hydration doesn't actually improve our model. So that indicates that that they're not very correlated with each other. If we did change that, so we could change hydration to be a stronger function of what are we trying to predict? Let's say the height. And if we try that again, we can see if our model will improve if we include these factors. So we see now for this different data set, we see that the intercept, these are all somewhat associated with the predictive outcome. And you see that because the null and residual deviance difference now is larger. So cumulatively, they have some effect, but it's not a very close correlation of their in terms of their each individual's factor. But this does indicate that how if we change our data set, we can identify different features of our model that can impact the outcomes that's of interest. And here's an example where you can see that there's somewhat small effects from each of them, and that might be something then to further explore with different models that are different from the binomial one. Okay, we'll talk more about this in the class itself. We'll also talk about the information criterion, which you get the 67.238 here. If we try this for the simple model, you see that the information criterion is larger at 69.9, and that indicates that this more complex model is more effective because you see a big fall in the AIC value there. The lower it is, the better, essentially the better fitting model, and it includes a penalty for the number of parameters that are present. If we look at a previous version for the more complex model, it was 71.06, whereas for the simpler model, in the previous version, we had 69.9 again. So in this case, adding another variable made our model worse. So that's important to note, and that's why the AIC can be instructive in terms of what's the best fitting model, including a penalty for the number of parameters that we include. So